Hi, this is Chris. Finally, at long last, I'm going to talk about how to derive the lookup table for the initial guess at the reciprocal value of a number. But I'm also going to talk about some issues peripheral to the lookup table. This diagram has been presented on numerous occasions. It shows the format of the IEEE 754 binary 16 format. The significand field of a binary 16 normal number can hold 2 to the 10th, or 1024 different values. If you examine the lookup table used in the Python code from the previous video, which computes the reciprocal, you would quickly find that the lookup table has 1024 entries. One entry for each possible significand value for a binary 16 normal number. As a reminder, the hexadecimal value 3C00 encodes the binary 16 value for 1. We know that 3C00 gets decoded as the quantity -1 to the 0th power times 1 point followed by 10 zeros times 2 to the 0th power. The smallest binary 16 value greater than 1 is going to be the quantity -1 raised to the 0th power times 1 point followed by 9 zeros followed by 1 times 2 to the 0th power. You should be able to see that the value we need to add to 1 to get this next larger number is the quantity -1 raised to the 0th power times 1 point followed by 10 zeros times 2 to the -10th power. I'm going to call this value delta. To generate the lookup table, I'm going to need a loop which does the following. We start by assigning the value 1 to d. Then while d is less than 2, we compute x, which is the reciprocal of d. We output the 7 most significant bits from the significand of x. And then we increment the value capital D by delta. One way to implement this loop would be to use the binary 16 class, which I wrote for the C++ code to compute the reciprocal. The problem is I didn't fully implement the class. This means I would need to write the division operator for the class and test it. That seems like too much work. All of us already have a computer which will do floating point arithmetic. I'm using a laptop with an Intel processor which supports the IEEE 754 binary 32 and binary 64 data formats. The question then becomes, how do I use one of these floating point formats to implement this loop? The loop above starts with the floating point value 1 and ends when the value of d is no longer smaller than 2. I started by figuring out what the values 1 and 2 look like when encoded as binary 32 values. This part is easy. The binary 32 value for 1 is encoded as the hexadecimal value 3F8000000, and the binary 32 value for 2 is 40000000. You might think that I then looked for the binary 32 encoding of delta. I didn't. I used what one of my favorite podcasters refers to as blunt force trauma. To increment the value of d, I treated it as an integer value and incremented it by 1, shifted left by the quantity 23 minus 10. No, really, that's what I did. Here the loop variable I holds the bit pattern for our current floating point value of d. The obvious question is, why encode d as an integer? Because doing so means I didn't have to figure out how to represent the value delta as a binary 32 value. I know that adding the integer value 1 shifted left by the quantity 23 minus 10 to I is going to yield exactly the result I need. Okay, I still need to perform a floating point division, so you're probably wondering how I accomplished that. It was really simple. I wrote really ugly non-portable code. Java has functions for interpreting integers as floating point values and floating point values as integers. In particular, Java has the function int bits to float, which takes a 32-bit integer and returns the 32-bit floating point number which has the same bit pattern. I implemented my own version of int bits to float using C++. So the first thing which the code does inside the loop is interpret I as a 32-bit floating point value. Now that I have a floating point value, I can use my computer's floating point hardware to compute the reciprocal for me. The Java function, which interprets 32-bit floating point values as integers, is called float to raw int bits. As you might have guessed, I implemented a C++ version of that function too. I used the function float to raw int bits to interpret the bits of the reciprocal as an integer. The obvious reason to convert the floating point reciprocal to an integer is that now I can use bitwise operations to extract the 7 most significant bits of the reciprocal significand field. The expression O shifted right by the quantity 23 minus 7, ANDed with the mask hexadecimal 7f, does just that. Having extracted the bits I need for my lookup table, I can print them in a suitable format. I'm not going to discuss the code in any more detail, but as usual, you can find the code on GitHub and sift through it to your heart's content. Like the Python code from the previous video, it's really horrible code, but again, it's not intended to be production quality code. It's a one-off program to generate a result and then be discarded. And some of you are looking at this code and saying, gee, that's overly complicated. And you are correct. I'm only human, so my first solution is often a poor solution, even if it works correctly. While preparing this video, I recognized how unnecessarily complicated this code is. I've reduced the code, which generates the table, to 8 lines of Python 3 code. It could have been even smaller, but I wanted the output to be nicely formatted. I bring this up to harp on what I've been saying in recent videos. One doesn't really learn new material until one struggles through the process of using the material. Seriously, if you're not trying to work through how to build a reciprocal circuit on your own, you're missing out on a great learning opportunity. Yes, I'm eventually going to present my own version of the circuit. Some of you just need a solution to your problem. And that's fine. I'm happy that you can copy my code into your workspace. But if you're really trying to learn circuit design, doing circuit design is part of the learning process. Thus endeth today's sermon. Because my version of the lookup table for the initial guess of the significand of the reciprocal has 1024 entries, one for each possible normal significand value, this raises an obvious question. Why did I bother using Newton's method? After all, since my table has one entry for every possible binary 16 significand value, I could have just looked up the significand value of the reciprocal and returned that. There are several reasons. The lookup table, as I've implemented it, uses 7 bits per entry. A lookup table which has the full 10 bits of the significand of the reciprocal would require 10 bits per entry. Using 7-bit entries saves a few chip resources for other uses. Secondly, if I simply looked up the significand of the reciprocal, the code wouldn't need to use Newton's method. And Newton's method is an important tool which will be needed for other circuits in future videos. Now consider the Python prototype code. It implements all of the rounding modes which must be supported for the IEEE 754 binary formats. If I pre-computed the significands for all of the binary 16 values, which rounding mode should I have used? You might say I should use the default rounding mode, round ties to even, but then I've tied the programmer's hands. I don't know what his needs are in advance. I think it's important to allow the programmer the ability to choose a rounding mode suitable to the problem he's working on. There's one last reason. A 1024 entry lookup table for binary 16 values is probably small enough that I'm willing to dedicate chip resources to it. But consider the lookup tables for binary 32, binary 64, and binary 128 values. One way or another, I'm going to have to limit the size of the lookup table and rely on Newton's method to get the additional bits of precision needed for these larger formats. It's time again for a study question. Let's say I wanted to implement a circuit to return the reciprocal of a binary 16 value using a lookup table. How would you implement the table so that the programmer could control which rounding mode was used to get the final result? In the next video, I'm going to prototype the circuits for the binary 32, binary 64, and binary 128 data types. Remember that the location for the code discussed in this video can be found in the comments section. Please share this video with friends and colleagues who might have an interest in this series. Questions and comments are welcome in the comments section. If you find this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks!